the chemical domain? The depressing answer is not really a great deal. But I think it's something that we should at least sort of talk about. This could be more of a discussion if people like. I'm happy to sort of take questions, people to interject throughout if that works better. Or into questions at the end. Either way is fine by me. Really, so what I've done is I sort of went through all of the sort of hardware experiments that have been done in the sort of chemical space over the last, since the first paper, sort of the sort of that 2 qubits simulation of helium hydride using a photonic chip. Since then, in the ensuing sort of like 13 years or so, there have been a bunch of simulations. But the issue is, what we can sort of see is up until sort of 2024, last year, the sort of majority of these simulations were dominated by variational quantum algorithms, which isn't surprising. The very first one there was a variational quantum eigensolver simulation. There are a few exceptions in there, notably Quantinium, for example, with the Bayesian phase estimation work from Kantaro. But by and large, variational algorithms were dominating through that period. I started my PhD in 2020 doing, you guessed it, VQE in the sort of chemical space. But in 2024, there was a paper released by IBM where they were doing this sort of new algorithm called quantum set configuration interaction, which it has some issues. We can get into the issues. But the thing that interested me was it was sort of the first distinct algorithm, if you like, from VQE that someone was running at scale on a quantum device. So you can see, all of these VQE simulations are sort of capped at about 12 qubits or so, whereas this QSCI simulation explodes into sort of the 7 to 7 qubit region there. And again, there are issues, but at least we can now start to address any of the sort of problems at some sort of scale to be at least competitive with sort of traditional electronic structure techniques. And then, these are some simulations that we've done in the group that I'm going to sort of present some of the work from those today. I guess I don't really need to go into this. Obviously, what we're trying to do is trying to simulate the electronic structure of molecules using quantum computers. The issue with that is that hardware is very noisy. And so in particular, we've worked pretty much exclusively with superconducting systems, which are incredibly noisy. So for example, this will look familiar. This is the heavy X lattice from that sort of IBM chips. So what we're doing here is we're sort of applying these sort of random Clifford unitaries U, and we're doing a Loschmidt echo. So we're applying U, and then we're sort of applying the inverse. And so if this was an ideal quantum computer, we should get a 0 state out the other end. But of course, these aren't ideal unitaries. There's some sort of noise indicated by these fuzzy unitaries here, which means that actually it's introducing some sort of errors into the system. And so the sort of depressing finding here is that so on the x-axis, we're increasing the circuit depth of these random unitaries. On the y-axis, we're increasing the number of qubits that we're using. And what you see is we get this sort of very rapid drop-off towards sort of the probability of measuring the correct bit string being 0.
Are these effectively many qubit unitaries, or just, the number of...
Yeah, it's they're sort of a combination of single and 2 qubit gates. They're sort of randomly sampled.
And circuit depth might not also mean circuit volume.
Sure.
Do they sample all of the qubits at each bit of the depth?
No.
Is that the worst possible thing? As in the thing that gives you the most knowledge?
You mean sampling all of the sort of idling qubits?
Yeah, so those U's are effectively overall the qubits, or do they just sort of...
No, so we're only measuring the sort of the subset of qubits that are actually applying the unitary Q here, rather than sort of measuring the whole system at once. This is also the other point to note is this is without any error mitigation whatsoever. So you can improve the sort of situation here. Applying error mitigation, you can sort of push this yellow region further up to the right hand side there. Ultimately, you're still going to, you're just kicking the problem down the road. Like you might get some slightly deeper circuits, but still this sort of probability of getting the correct bit string is going to decay very quickly. And so algorithm design, it needs to be needs to take these issues into account, and that's sort of the difficulty here. So here's sort of a few popular algorithms that are run in chemistry. Obviously, phase estimation is what we want to be doing. There are actual theoretical speedups associated with it. The measurement overhead is constant. The issue is we get some very deep circuits, and so that's why we can't. Aside from small simulations like the Bayesian phase estimation, which was 4 qubits, that's it, something like that. 2.
That's 4.
Okay.
Anyone with 20.
Nice. Yeah, aside from that, seeing that this is what's driven sort of predominantly people looking at VQE, at least sort of in earlier days of the development of these algorithms. The reason being is you can get away with shallow circuits, but it brings with it a whole bunch of other issues, namely the actual energy estimates are noise prone, and also, whilst in phase estimation we have this sort of constant measurement overhead, we've now traded those deep circuits for now a much larger measurement overhead. And so before getting into the QSCI side of things, as I mentioned, I sort of got into this first doing VQE, so I'm going to go into some of the work that we did there. I guess people are familiar with VQE, right? Some sort of quantum subroutine within a classical optimizer. You can define like gradients and things that inform the updates of your circuit parameters. And so this is sort of typically what you see in like an energy trace from a VQE simulation. There are a bunch of different curves here. The sort of black one is after we've applied some error mitigation techniques, which we can sort of talk about a little bit. And what we're doing here is simulating the sort of anti-ferromagnetic Heisenberg model on this Kagome lattice here. But again, going back to sort of the issue with noise there are a bunch of different considerations that you need to take into account to actually run some successful simulations here. And so the ones that I've looked at are resource reductions, that's sort of designing qubit reduction methodologies that sort of allow you to go into a subspace of the problem and alleviate some of the burden on the quantum hardware. Obviously, the circuit construction you need to be sort of thinking carefully about, and then finally error mitigation. So let's go through those sequentially. Each of these could probably be its own talk, but I'm just going to sort of go into it in sort of a high-level overview. First, we have these qubit subspace techniques. So specifically, the one that I've worked on a lot is this idea called contextual subspace. The idea being is that you sort of try to exploit this notion of measurement contextuality, which in a sense is, colloquially is sort of like where the quantumness of your problem lies, is in this sort of measurement contextuality. And what it ultimately comes down to is sort of contradictions in the assignment of definite values to sets of Pauli observables. And so what you can do is you can build up these sort of graph networks and sort of identify where these regions of contextuality are sort of most prominent, and you can sort of divide your subspace methodology around that. So here's just a sort of small toy problem. This is sodium chloride. On the x-axis, we're increasing the size of the contextual subspace and looking at the FCI error. And so you can see, for example, here, by the time you get to like, what is that, like 13 qubits or so, you're within sort of a high accuracy. I don't want to say chemical accuracy, but sort of in that sort of algorithmic accuracy that people are aiming for. There's this graph in the middle here, and that's indicating what the sort of, so we have this idea of contextuality. What it actually comes down to is sort of the non-transitivity of these Pauli measurements. So maybe we can go into this if people want. Are people interested in going into these tables, or do you want me to continue?
Yes.
Okay. Okay, so let's start at the beginning. So we've got this top right-hand one here. This is a sort of classical game, and the objective is to fill this grid with +1 or -1, such that the products along the rows give you a +1, and the products down the columns give you -1. So you might start filling this grid out, satisfying the first row, the second row, etc. But you're always going to find that you're going to get to a point where you can't fill one of these points, because if you look at the sort of row products here, we want this to be a +1, so we have to put this in with a +1. But then to satisfy the column product, we would need this to be -1, so that's -1 to -1, we need this to be -1. So it's not possible to fill this grid such that we satisfy both of those conditions. However, if instead you play this game with bipartite Pauli operators, it turns out you actually can satisfy this grid such that the row products give you now plus the identity, and the column products give you minus the identity. Okay, and that's because of this sort of rich algebraic structure of the Pauli group. That's sort of a seemingly inconspicuous thing, but actually what you sort of realize is that when you take, this is a set of observables that can feasibly go into a lab and measure. And so what that sort of reduces to is that when I take the measurement of these things, I'm going to get back a set of +1s and -1s, and that's sort of like you're superimposing this grid on this grid. But we already know that we can't satisfy this grid, and so there's some sort of a contradiction here. And what it comes down to is the sort of context dependence of measurements in quantum mechanics. And so what we mean actually sort of explicitly by context is a set of commuting observables. So if you look along the rows, you see these all commute, these all commute, and these all commute. Likewise, going down columns, these are sort of commuting sets of observables. As a commuting observables, we can assign sort of values to simultaneously, but as a whole, we can't do that because there are these. What it turns out to reduce to is if you look at this sort of top left quadrant here, what is it? This commutes with that, this commutes with that, this commutes with that, this commutes with that. So you get this sort of like square grid, and it turns out that this sort of non-transitivity, by which I mean that commutes with this commutes with this, but that does not commute with this. Right, we don't have this like triangle of equivalences. And so this is where the sort of breakdown of measurement contextuality comes from. Conversely, you can then ask the question, what does a system look like that doesn't have this sort of contradictory behavior? Obviously, if you just take a commuting Hamiltonian, you can assign values consistently there, and that is a classical problem. But actually, you can go a bit further than that. So that's what we're showing here. This is the graph structure of what we're calling a non-contextual Hamiltonian. So it turns out, if you just stick this bit in the middle, that would just be a commuting Hamiltonian. But it turns out you can actually have these sort of additional commuting cliques, which are sort of disjoint from each other. And that still allows you to sort of assign values definitely to this Hamiltonian. You can write down a classical objective function that corresponds to the sort of energy spectrum of this thing. But the idea with contextual subspace is you identify a subset of the full Hamiltonian, which is this big cloud of terms, extract out a non-contextual piece, solve that classically, and then you can sort of reintroduce quantum corrections on a quantum computer by then sort of reintroducing interactions with the contextual piece of the problem. So it's kind of the way to think about this is it's like you've replaced your Hartree-Fock reference with now a non-contextual reference, which is guaranteed to be at least as good as Hartree-Fock, but in many cases will be better, especially in some strongly correlated sort of regimes. And so this is sort of the idea behind this contextual subspace sort of method. Okay, so I'm going to show a sort of simulation using that in a second, but the other considerations that need to go into running a successful simulation are the circuits you're constructing. And so there are various considerations here. You want to try and encode your chemical symmetries into the circuit. This is a bit more nuanced in the contextual subspace picture because you're sort of projecting the problem into a subspace. And so Hamiltonian is now sort of quite abstract. It's not as clear what those symmetries are anymore. Turns out it's actually not a problem. You can sort of project your symmetries into the subspace as well, and you can still make sure that you're satisfying those properties. And the other thing is if you're actually running on real hardware is you've got to be thinking about the hardware topology that you're mapping onto. So this is some work that we did where we were looking at a sort of hardware tailored, sort of hardware aware circuit construction. This is sort of an example of adaptive EQE. So regular adapt to these sort of triangles, and you can see, as each time we're adding a new excitation to the circuit, and the number of CMOP gates in the sort of final transpiled circuit is increasing quite rapidly. In this case, transpiled for this 12 qubit ring, which would be the sort of ring you'd find on the heavy hex lattice. But actually, we found that you could sort of try and introduce some sort of hardware awareness into this process. And the way that we did that was sort of, without going into too much detail, sort of looking for approximate subgraph isomorphisms with the target hardware graph between the circuit. So for example, this is just a fairly arbitrary circuit, and sort of the qubit coupling graph looks like this. If you want to try and map that onto this thing, you need to use a lot of swap operations to do that. And so yeah, through this sort of hardware aware biasing, what you can see is we're getting same level of sort of accuracy here, but at a sort of substantially reduced circuit depth.
I mean, this sort of thing.
Yes.
Effectively, you're changing your selection algorithm for the extra QSCI into the sets. Could you have just and that's been targeted towards the hardware, so you don't even really see lots of effectively. Yeah. But you could have randomly found the same set if you without the hardware aware. It's just that
Yeah.
The likelihood of doing it would have been low, is that right?
Yeah, no, for sure. I guess you could sort of, yeah, if you got lucky, you certainly could do. It's just that we're introducing sort of an additional term into the sort of that adapt like cost function to try and bias towards these. And it's not just each term by term; it's sort of considering all of the previous excitations you already have in your circuit, because obviously that's going to sort of.
Is it different to changing your initial operator? Would you just have an operator for that as hardware?
So it comes back to that same problem in that it's not just a function of the individual terms, but also the terms you've already included in the circuit, if you like. So it's like you have a graph like this, I'm going to add another excitation, it's going to introduce more edges into this graph. And so it's sort of this problem of trying to, at each step, trying to make that graph look as close as possible to sort of target hardware graph. And then the final sort of ingredient here is error mitigation. We use a bunch of different techniques, but there's sort of one that does a lot of the heavy lifting, and for a lot of other researchers is zero noise extrapolation. Sort of counterintuitively, the goal here is to actually introduce more noise into these already very noisy systems. The idea being is that if you can introduce that noise in a really careful and controlled manner, you can make some sort of inference on the sort of behavior of that noise and try and extrapolate to this magical point of zero noise. And so the way that we choose to do this, there are a bunch of ways that you can introduce noise into a quantum system. As an aside, I recently found out that the Cleveland Clinic in the US, they actually have one of IBM's systems on their site. I assumed it was going to be in some like really controlled environment, locked in some back room somewhere. It turns out it's actually just sat in their cafeteria. So on the topic of introducing noise into a quantum computer, I guess, yeah, put it in a cafeteria and let people eat their lunch around it, I guess. But the way that we do this, you can do things like stretching the pulse durations in your circuits. There are these sort of discrete approaches which sort of it's called unitary folding. This flavor is slightly different to a lot of the ways that people do unitary folding, in that a lot of the times people will just introduce sort of a unitary and its inverse and sort of tile it in the circuit. That could be as simple as just adding like pairs of C-naughts after each C-naught gate in the circuit. The approach that we've taken is to decompose all of the C-naughts into a product of controlled phase gates. So what you can see here is these phase gates in the middle. The sort of rotation angle is going to be getting smaller and smaller as we increase the number of repetitions, but the sort of overall action of them is going to be a C-naught gate. One caveat being is that when you actually transpile this for a quantum computer, it's going to be transpiled back into whatever the native gate state is, which in this case is the 2 qubit entanglement gate was again C-naught. So these phase gates are going to become 2 C-naughts per phase gate here. And so just to show what that looks like, this is a small 5 qubit contextual subspace example. This is sort of adding all of those ingredients together. We use the hardware-aware adapt routine to build these circuits. And yeah, what you can see, the nice thing about this like phase product thing is the issue with just like adding pairs of C-naughts after each C-naught gate is your sort of like 0 C-naught point, if you like, is sort of shifted in that your base circuit has, say your base circuit is 1 C-naught gate, then the next noise extrapolated one has 3 C-naught gates, then 5, then 7, etc. And you want to extrapolate to effectively 0 C-naught gates, if that makes sense, because that's where there's no C-naught noise. The nice thing about this is actually you don't have this shift, like the 0 point, sorry, the 1 noise point would have 2 C-naughts, then 4, then 6, then 8. So extrapolating, you get to that like theoretical zero noise point. What you can see is actually this works quite nicely. So this is again a VQE energy trace. Ignoring the bottom line, these are the sort of noise amplified curves. And they're sort of quite well behaved, which was quite surprising to see. We did use a bunch of other techniques like dynamical decoupling, symmetry verification, measurement error mitigation on top of zero noise. But the nice thing is that you can see when we extrapolate here, we're actually getting very close to the noiseless curve, which is that sort of lighter cyan blue color. So yeah, finally putting that all together, This is the actual final potential energy curve. So this VQE simulation from the previous slide is for the rightmost point at 2 angstrom separation between 2 nitrogen atoms. But actually across the whole potential energy curve, we're getting pretty good results. The thing that's found quite nice is that actually as you get into these stretch regimes, because of this non-contextual, okay, we can get into the non-contextual curve, but because of this contextual subspace thing, it's sort of capturing that sort of strong correlation quite nicely. The thing that's exciting is it's sort of comparable. Of course, these QSCI calculations, SSCF calculations are very good, but we're still providing the same sort of qualitative description of this one-breaking process, actually at a much smaller subspace size compared to those CAS spaces. So, for example, looking at this largest CAS space has 7 spatial orbitals at 14 qubits, so that's like nearly 3 times the size of our 5-qubit contextual subspace. There is this weird non-contextual curve, which has these discontinuities in it. This is sort of showing what I was trying to sort of alluding to before, in that this sort of idea that it can capture some sort of static correlation in the sort of non-contextual solution. So you can see up until this point, where it's sort of predominantly dynamic correlation, it's pretty much tracking arbitrary Fock. When we get to this point, then we get this break, and this point of discontinuity. It actually lines up perfectly with one of these CAS spaces here, and then again, we sort of get another break there. This could be related to like the Colston-Fisher point or something along those lines. But it would be interested to do sort of further sort of investigations of that. Yeah, that's something interesting to note. Okay, great. So that was this work. And going back to the big graph of all of these practical simulations. I didn't go into the first one. That was sort of a smaller 3-qubit simulation, also using contextual subspace, but in that case, simulate HCl. Okay, so moving on. So we've spoken about VQE. You saw that as a 5-qubit simulation. It's quite difficult to scale VQE beyond that point. There are some 12-qubit simulations. I think there was one a bit more recently, which was maybe up to 15 or 16. Maybe there might be more since that I'm not aware of, but regardless, there are some sort of inherent scaling issues with VQE. So that's what's sort of inspired this shift towards QSCI, it's quantum circuit configuration interaction techniques. You can still get away with the shallow circuits of VQE, but whereas VQE energies are very noise prone, right? Any noise in the circuit in the hardware is going to sort of directly affect the noise in your final sort of energy estimates, and therefore requires a sort of very heavy error mitigation. In QSCI, you're sort of using the quantum computer as a configuration sampling machine, effectively, and so then you're projecting the Hamiltonian into the subspace bound by those configurations, and then that's solved by sort of classical diagonalization. For that reason, there are some inherent scaling issues with QSCI, but it does mean it's noise resilience, right? Noise only affects the quality of the subspace, not the quality of the energy estimates. And then there are some open questions. There's not a lot of theoretical sort of framework around QSCI yet. There are some issues with circuit construction, and there's questions as well over the sort of measurement overhead that's required. But let's get into it. Like I said, I didn't need to explain configuration instructions to you guys, but just to set the scene. Different configuration interaction methods are sort of, I guess, differentiated via the way that you choose to select your subspace of electronic configurations. Obviously, in the sort of limit, the sort of completeness limit, we get full CI, where we're considering all possible electronic configurations. We're given them particles in a number of orbitals. We can make restrictions to sort of, that scales exponentially, of course, but we can make restrictions to get something that's sort of polynomially scaling. So we consider New Zealand double excitations. We can go into a sort of subspace of electrons and orbitals, again, exponential scaling, but now it's in the sort of size of that, and we can control the size of that subspace. And then finally, the sort of flavor of selected CI is where we actually have a bit more flexibility over the way that we're choosing to include electronic configuration in these sort of diagonalization calculations. And so one of the most successful of these is Heatbath configuration interaction. But the idea here is we start with some reference states. That might be the Huxley Fock state, for example. We effectively hit it with the Hamiltonian. We can track the Hamiltonian onto it and we see what configurations fall out the other end. So in the first iteration of this, we're going to get single and double expeditions. We're going to project into the subspace. This is the projected Hamiltonian here, and we're going to diagonalize that with a large amount of sort of conventional HPC resource. We're then going to iterate this process, iteratively contract Hamiltonian, which is quite expensive. And each time, this is going to refine the sort of wave function that it's producing. Is sort of a very sort of basic example where you can see as for subsequent iterations, at first we just got through Fock, then we get a sort of break here, and the sort of as calculation is allowed to iterate for sort of longer, we get sort of we eventually recover the configuration interaction energy. It's guaranteed to do that if you allow this process sort of run as long as it needs to. The idea of quantum sector CI is quite simply just to replace that like Hamiltonian contraction step with something that your quantum computer does. What that something is, sort of where the sort of QSCI design piece comes in. But ultimately, the idea is to use this quantum computer to spit out electronic configurations, and then the process is the same. You might then update your circuit in some way based on the output from this classical diagonalization, or you can just do a one-shot, which a lot of the work that has been done already does. As I mentioned before, these energies are now robust against noise, and it's only the subspace quality which is going to be affected. Issue number one, there are quite a few issues with QSCI. The first one is the design of the circuits. It's quite nuanced in the sort of case of QSCI. So in V3, for example, ANSAT's design is still a difficult problem, but at least there's sort of a direct correspondence between the circuit that you run on your quantum hardware and the energy that you get at the end of the day. The issue with QSCI is, whatever circuit you're running on the quantum computer, because there's this classical diagonalization step afterwards, that sort of you lose that sort of direct connection between the circuits and the final wave function. And so that's an issue. For example, in VQE, you need to be able to then define your parameter gradients, for example, to make your next sort of parameter updates. And you can do that easily in VQE, but in QSCI, that's not possible because, for example, imagine your QSCI circuit is sufficiently expressible such that it can express whatever your final wave function is, which already is quite a strong assumption. But at least what that would say is, okay, there exists some point in the sort of image of this sort of parameterized circuit that expresses your sort of QSCI solution. I don't know where that point is. But I've somehow managed to obtain this wave function, and I can calculate gradients and things from that wave function, but I don't know where that point is in the space. And so you want to, in QSCI, any sort of like approach that requires parameter updates, for that reason, it's quite sort of ill motivated. And so for that reason, you've got sort of the initial approach with these sort of local unitary suggestros, which sort of impose these locality constraints. I mean, in some senses, it's sort of like a local approximation to UCCSD kind of. And so this is what a lot of the initial work does. So, for example, these are some screenshots from that IBM work, which was actually published in Science. And what you can see is looking at these heavy hex lattices. What they do is they sort of they have an alpha block and a beta block, which are like these red and blue, and they sort of go down the diagonal of the chip, and then they spill out into the off diagonals here. So within each of these sort of separate regions, they have a bunch of Gibbons rotations that do sort of alpha to alpha excitations or beta to beta excitations. Then they have these ancillary qubits, which are these green ones, which induce some sort of density couplings. That's quite restrictive, and the issue with LUCJ is you sort of initialize it from the like classical CCSD amplitudes, and so without doing any subsequent quantum optimization, there's sort of a bit of a question as to whether there's any feasible sort of, are you just sampling from a conceptually classical state at that point? Is the sort of one of the criticisms that approach had. More recently, there have been sort of approaches based on Hamiltonian time evolution, which I think are a bit more promising, sort of equivalently quantum Krylov approaches. At least here, these are now sort of inherently parameter-free, right? And so this is the way of sort of probing classically inaccessible distributions in principle. sort of inform your configuration selection step.
They still depend on the initial state, present.
They
Slightly
still-
large fault, but-
Absolutely, yes, exactly. So you still get that same issue. Same issue is present in phasor summation. Is getting that sort of initial reference state that has some sort of non-zero overlap with the ground state. Is always sort of swept under the rug, but yes, it is a big issue for sure. This is a silly example. But the reason I did this was more for the story, in that the first, as we mentioned before, that was that first 2 qubit simulation of helium hydride. Just sort of demonstrate where we've sort of come in the sort of ensuing decade. Was I wanted to do complete basis set extrapolation on a quantum computer for that helium hydride system. It's a bit silly because it's only got 2 electrons. And to be completely honest, in that 120 qubit simulation, it's pretty much just sampling noise at that point. And so it just speaks to the simplicity of the problem, that we're still getting good results from just sort of randomly sampled noise effectively. But at least what you can see is so these are sort of errors within each of the basis sets here, double, triple, quadruple zeta basis sets, compared to sort of MP2. At least we're doing better than MP2 is, I guess, the best thing that can be said here. This sort of, with these open boxes, is the sort of extrapolated energy. And so a big goal of mine is to exceed 100 qubits. I don't really want to say that this has done that. But yeah, it's just sort of, I guess, a bit of a toy problem.
So as you go down those levels, how
Yeah.
much more expensive is it to do the classical bit?
Classical bit. Yeah, so this is a big issue with QSCI is, you're always going to, what all CI methods really is, you're always going to run into that wall in terms of how large a system you can diagonalize.
But it is only 2 electrons, so that's
It
probably.
doesn't need 2 electrons, so this is fine. You can run full configuration interaction at the 5Z sort of quintuple zeta basis set level. So yeah, the sort of the combinatorial degrees of freedom are very low. I guess the thing is, for a fixed subspace size, the problem is, I mean, we know CI is not scalable, right? So I guess the question is, for a fixed size of subspace, what is sort of the best possible set of configurations you can include in that subspace? And that's, I guess, kind of the goal of these SCI methods.
As you're going through adding more and more determinants to the SCI.
Yep.
How many times do you pick a determinant from your quantum selection that you've already got?
Yeah, absolutely. And this is actually on a slide a bit later on. But yeah, that's one of the sort of main criticisms, is this repeated sort of sampling issue. Yeah, but before we get to that, this is just one more sort of little case study that I wanted to show that me and some of the other people in the group at UCL did with LRZ and IQM. We're sort of seeing in the last year there has been this sort of trend of integrating quantum resources into sort of HPC centers. So yeah, here from this is a 20 qubit IQM chip which they have on site at LRZ. My professor likes to say this is like a flea in the elephant situation, where we have this little 20 qubit system which is coupled to SuperMUC NG, which is a massive supercomputer. So yeah, it's kind of funny the sorts of problems that get offloaded onto this compared to then what you can do with a supercomputer of that sort of scale. So the problem that we wanted to look at here was sort of look into this Grotthuss mechanism, sort of proton hopping between water molecules. There's sort of 2 sort of widely believed sort of manifestations of the sort of excess proton in water, the eigen and Zindel cations. The one that we looked at was the Zindel cation because it's smaller. And so the goal here was to simulate this proton hopping. Here's just some sort of classical simulations looking at the sort of potential energy barrier as you sort of stretch the separation of the 2 oxygens. I guess it's just sort of to look at where the sort of optimal sort of proton transfer is going to occur. So I guess is when this well is sort of flat and you don't have that barrier to stop the process. But also because we were coupled to SuperMUC NG, we needed to do something on the HPC as well, not just on this IQM chip. So the natural thing there was to do sort of QMMM, to have sort of this quantum mechanical simulation embedded within a larger molecular mechanics sort of classical environment. And so what we did is we threw more water molecules at it. So we have this Zindel system, which you could just about make out in there, which is surrounded by an environment of many more water molecules. And so the superconductor, this is still a tiny system, but we are very much not utilizing. I think we're utilizing a fraction of one node on supermech. There is a goal to sort of scale this up to actually make use of a larger chunk of the supercomputer. But here, this is more of a proof of concept, so that we can actually do it. And yeah, finally, so here we have so there's supermech on the left. That's what's handling the sort of MD calculations. That's sort of propagating the positions of these water molecules around this quantum mechanical region. And then we have our sort of little Zindel system in the middle. We actually use the technique which I probably won't go into, but this is called projection-based embedding, which other guys in the group have worked on a lot. The idea is to have a sort of higher accuracy wave function method embedded within a lower accuracy DFT calculation. So we have sort of this sort of onion situation where we have molecular mechanics on the larger scale. Within that, we have a DFT calculation, and then within that is where the sort of quantum computer is simulating, in this case, just two oxygens and a proton in between them. We then did qubit tapering on top of that. So I think we went down to like a 16 qubits problem maybe to actually run on the hardware, and it's a 20 qubit system. What we did is, so we've got the Hartree-Fock energies here. So this is where the proton is sort of localized between the two oxygens. So I think on the right-hand side here, that's when the proton is sort of symmetric between the two. And then here it's sort of localized on the oxygen. What we can see, so this is a bit surprising, is actually the QSCI results, which are these ones in yellow, were outperforming a DMRG calculation. In this case, the DMRG calculation is what we used to actually seed the quantum to the QSCI calculation. So we used sort of NPS to circuit mapping to take that state and sort of prepare it on the quantum computer, and then sampled from it for the QSCI calculation. We suspect it might just be that the noise is actually working in our favor in this case. Which actually, if you look at the literature, there are some crazy claims where people are actually like embracing the noise for QSCI, but the issue is these are sort of small simulations, and so you get that a lot more often. I don't think those such arguments will hold as you sort of go to larger and larger systems.
How big is the Hilbert space that it's sort of your SCI is in?
This was a 16 qubit Hamiltonian.
16 qubit Hamiltonian.
Yeah.
So.
What is the method for the ground truth on that graph? Did you just do FCI? Or?
This was FCI. Well, so it was FCI in DFT in yeah, it wasn't like it wasn't the sort of full system, as in full Zindel system FCI.
So was it just a really cheap DMRG calculation?
Yes.
Okay.
Super late one dimension. Yeah, exactly. Yeah, so this is more of a proof of concept, I guess. And yeah, as I mentioned, we are interested in sort of, because we have access to these resources, is sort of scaling up to the classical side of this, and actually looking at some more interesting sort of systems from a sort of biochemical interest point of view. And so we've got some people who are looking into what systems could be of interest for us to look at. As it stands, yeah, this is sort of a funny sort of, yeah, as my professor says, flea in the elephant situation. Okay, back to this plot. So we've now moved on. This is this work. We've now gone up to the sort of, okay, it's not quite 16. Okay, it might have been a 14 qubit simulation actually. But now we sort of, before we were sort of right at the cusp of this sort of transition from variational algorithms to QSCI, I think that was a bit of sort of VQE fatigue at that point. And that's probably why there's been this proliferation of QSCI work. And now moving on to this problem, this sort of the criticism that you raised, Alex, is this issue of repeatedly sampling the same determinants. And this was articulated in a work from Reinholdt, and they actually addressed that they sort of raised a number of issues with QSCI in that work. The first one indeed was this problem that you are probably going to sample the same determinant a lot. For example, if your problem is dominated by Hartree-Fock, you don't want to waste 90% of your samples just sampling the Hartree-Fock state over and over again. The sort of rebuttal to that a lot of people, for example, the rebuttal that IBM gives to this is actually you don't need to prepare, the ideal QSCI circuit isn't necessarily the FCI states prepared in circuits. What you actually want is more of a sort of even distribution over these sort of important by some metric configurations. So if you were able to prepare an equal superposition of all of the high sort of weight terms in the wave function expansion, that would be a great QSCI circuit. And so actually doing that in practice is hard. I don't know how you would construct a circuit that would guarantee that would happen, but that sort of at least casts a little bit of an aspersion on this problem of sort of sampling the same determinant. There are other approaches that we're looking into to actually sort of suppress, if you know, for example, Hartree-Fock state is going to be prevalent, and we're looking at ways sort of to suppress that within the circuit. Yeah, it's a very valid concern. And then the other one, which sort of leads on from this, is that, okay, say for example, you are able to construct a circuit that prepares this nice uniform superposition of important electronic configurations. They then argue that even in that situation, you're still going to get less compact sort of CI expansions compared to Heatbath configuration interaction. And then they have these are a few plots taken from that work. So you can see so on the HCI side, it's the blue and green curves. The blue curves are initialized from Hartree-Fock, whereas the green curve, I think, it's initialized from like an antiferromagnetic, like around the sort of iron is like an iron sulfide cluster, I think. Sort of have the spins of antiferromagnetically aligned around the iron. So that you can see that's a better starting point than Hartree-Fock in this case. And then these red dots are these sort of QSCI results, which, yeah, as you can see, they're doing a fairly poor job by comparison. I guess they start off doing better than Hartree-Fock, but the convergence is quite slow towards the QSCI energy. And so finally, these are really legitimate concerns that do need addressing, but they're currently sort of based on numerical evidence. So that's something that I would really like to see in sort of QSCI, sort of a bit more of a sort of rigorous theoretical treatment, which we haven't really seen yet. There are sort of a few works that try to make some sort of progress towards that. So for example, there's a work from IBM where they sort of try to prove some performance guarantees and convergence guarantees for QSCI. That doesn't address these issues necessarily, it just says that it will converge at some point. And then there are some works which try to show that LUCJ circuits are classically hard to sample from, which is sort of contradictory to some of these claims, I would say, but by and large, I think there needs to be a lot more sort of theoretical development around QSCI. Actually, those criticisms apply even before we consider noise. So we're back to this same plot again, where we're looking at the sort of drop-off of the sort of fidelity, well, the probability of measuring the zero state in that case. This is the fidelity of preparing GHZ states on, I think it was the IBM Eagle chip from a couple of years back. This picture might be slightly better now, but it would probably still be sort of somewhat of a decay as we sort of increase the number of qubits in this GHZ state. So the issue is, right, ignoring the issues that Reinhold raises, even without those problems, noise is still going to sort of push us outside the sort of desired symmetry sector for our problem. So for example, we're going to get bit flip errors. It means for large problems, it's going to become sort of increasingly unlikely that we're going to sample anything in the sort of correct particle sector, for example. And so when we already have this concern of the sampling overhead, if we're also throwing away loads of those samples as well, that's sort of not a good situation to be in. And so this is sort of where I then raise the question, is there a different way of using those samples as opposed to just using sort of the raw measurements to define subspace to inform some other sort of hybrid configuration sampling scheme? Like, can we inject some sort of information from the quantum device into, it might even be like an HCI style sort of selection criteria, But if we can at least inject some sort of classically inaccessible information into that process, is there a way of sort of improving on the convergence rate of HCI, for example? And this is still very much sort of work in progress. This is sort of the first approach that we took. And it's to look at these sort of orbital occupancies of a time of, under sort of time evolution of some quantum state. And so even though we still have this issue of bit flip errors, if those errors are somewhat stochastic, i.e. the error source is sort of incoherent, then there is still hope that we could potentially average over those bit flips to still discern some sort of a sort of signal of some sort of occupancy feature in the sort of occupancies of that measured states, if you like. And then using that information, try and develop some sort of a sampling protocol that makes sort of leverages that data. So looking, for example, here, these are 42 qubit time evolution experiments. In this case, this is a silicon tetrahydride system in a 631G basis set. And so ignoring this top left-hand one, that's sort of occupancy from the final diagonalized sort of QSCI wave function. But here we're starting with effectively a Hartree Fock state. You can see that that gap at the Fermi level. As we evolve for more time, you can still discern this gap, but we're getting a sort of a bit more not well. It's hard to know if it's just noise or if there is actually some sort of physical feature present there. Here you can still just about make a bit of a jump around about the gap there, and then beyond that point, it sort of turns into quantum mush.
What would the fully just noise thing look like? Would it just look like a?
So full noise would be just uniform on this dotted line here.
So it's not just noise.
It's not just noise. It is sort of interestingly peaked at the Homo-LUMO gap. That could be completely sort of coincidental. But what that does mean is it will sort of, so this sort of configuration sampling protocol that we developed, what it does is it sort of looks at these distributions and tries to predict what excitations would be most likely to occur given this occupation sort of distribution based on sort of configurations that you already have within your subspace. And so, because this is peaked, slightly peaked, what that's going to do is it's going to sort of preferentially select excitations around the Homo-LUMO gap here. But again, that could be completely coincidental that we do get that peak. Actually, if you look at the error, the sort of scale there is between like 0.021, 0.025. Like it's quite a small difference in probability. If you plotted these all on the same scale, this would look quite flat by comparison to like this, for example. This was just sort of a first idea. Like I say, this is this silane, so silicon tetrahydride system. In this case, we're still using an IQM chip. Before it was a 20 qubit one that we did with that work with LRZ. This was done directly with IQM, and this was a 54 qubit chip. So you can see the layout of the qubits there. So IQM uses a square sort of lattice as opposed to IBM's heavy hex. That said, IBM is bringing out a square lattice. They say by the end of the year, although they're sort of running out of time to do that. And this was a sort of LUCJ layout. That's not what we did for the simulation, but this was to show like how you might lay out the qubits for LUCJ, where you have these sort of alpha and beta blocks. So if you remember from before, IBM sort of goes down diagonal and spills out. And the issue there is that when you spill out into the off diagonals, it's very difficult to get couplings between those sort of opposite ends of the chip. Whereas here, because it's a square grid, for example, it wouldn't be too crazy to believe that you could get this qubit coupled with sort of that qubit over there, for example. These are placed such that the Homo-LUMO gap sort of lies somewhere in the middle of that sort of density coupling region down the center of the chip. And you also note there are a few missing couplings because this was sort of an early revision of the chip. There were a few qubits that didn't want to play ball. Ultimately, so that was so we did this time evolution thing with this occupancy biasing of the sort of sampling scheme. Maybe, yeah, we'll get to the convergence. So a few curves on this plot. So on this sort of horizontal line is the converged HCI energy. We have these like burgundy diamonds. These are the QSCI calculations. These black boxes it's an SCI protocol, but the sort of basic ones, not as good as HCI. So that's sort of the like, naive dialect in PySCF. We then have this dashed line here, which is the HCI calculation that was done using PyCI. And then this sort of multicolored curve that's been QSCI results. So the first thing to note is we beat the basic SCI protocol. Yeah, that's a good start. We do better than QSCI at sort of large subspace dimensions. HCI is still king here, is the main takeaway, but if you squint, we're not too far off in some places. Scarily close here, for example. So I'm confident because this was sort of a very sort of early experiment of the sort of idea of what we might want to try and do here. We have some ideas for how we can sort of take this further and introduce more sort of information from the quantum computer into this sampling process. And so my dream is that this curve will cross over HCI at some point. We haven't seen that yet. I don't think anyone has seen that in the literature, as far as I'm aware. I think that's sort of the one to beat is, if QSCI is to be taken seriously, it needs to be at least do better than HCI, which is a formidable target, but that's sort of what I'm trying to do at the moment. One thing to note is we sort of did a bunch of other things in this work. So here we were looking at not just the QSCI energies, but also these sort of Epstein-Nisbet perturbations on top of those. I like this plot because it's very satisfying the sort of the linearity of these sort of curves. So on the x-axis we have the second order EMPT2 correction, and on the y-axis we have the QSCI energy. And there's the sort of the correction term is that. And so the observation there is, of course, as the configuration subspace approaches completeness, this perturbation term should go to zero. So it sort of motivates some extrapolation scheme here, where we can extrapolate to the 0 point. We like 0 point extrapolation stuff, I guess. You can then take this as your sort of SCI approximation. And so that's what these are the final results. A bunch of other wave function methods now plotted alongside, maybe slightly hard to see. But I guess the most important one is the error plot at the bottom here. These errors are taken with respect to HCI, the converged HCI calculation. A bunch of different curves here, but these sort of final extrapolated, extrapolated to the sort of zero perturbation point is these sort of squarish diamonds in this purple color here. So you can see this is that sort of region which we don't want to call chemical accuracy, but sort of within 43 millielectron volts or 1.6 millihartree error of, in this case, the HCI energy. And it's sort of within that region, apart from this annoying point here where it just dips outside that threshold. But at least we are sort of within that sort of error tolerance of the HCI reference in this case.
Above or below? I mean, in principle, they could be above or below.
They could be below, they're above. In this case, it's slightly easier to see in this plot.
Yes.
You can just about make out, so this solid black curve is HCI. The SCI one really struggles, this is the naive SCI, so really struggle to converge here. And then here we have sort of our raw QSCI plus second order perturbation, and then the sort of extrapolated the zero perturbation energy is just I think it might dip below HCI at this point maybe, but only by a hair.
When you say naive SCI, do you mean like naive QSCI or something
Naive
else?
SCI. So it's the sort of implementation in PyCF of selective configuration interaction.
Okay.
The issue with it, the reason why we see this slow convergence is I think it doesn't allow you to take arbitrary alpha beta excitations. It sort of does like a Cartesian product of alpha selections and beta selections and then sort of multiply them together. So you get a sort of quadratic overhead of sort of potentially redundant configurations, whereas HCI has sort of much more flexibility to address the alpha and beta excitations sort of individually. I think that's why that sort of the naive approach is sort of quite slow to converge.
With your extrapolation, you should be able to get an error bar.
Yes.
On the fit. How
Sure.
big is that error bar approximately?
Good question. I'm not sure. That's definitely something I could do.
Yeah, because they look like pretty, as you said, pretty good linear bits. So you might end up saying, well, our best estimate has quite a small error bar.
Right.
In these things, which is.
Yeah, that's true. No, I'd be quite keen to see actually what the errors are like. I will do that actually. Nice, yeah, I think that's everything actually. So that was the final work from sort of what we've done in the group. I think the next one's going to be a sort of more of a, well, as I said, I'm quite keen to exceed that sort of 100 qubit scale. No one has done that in the chemical space yet. I'm sure IBM is rushing to get there. We do technically have the 120 qubit simulation of helium hydride, but I don't want to claim that. And so yeah, just to sort of recap and to end, there's still some outstanding issues with quantum steps configuration interaction. It's still not clear if it's going to get us to any sort of quantum utility or even advantage, even though it's a slightly can be a bit of a dirty word sometimes. But we need better circuit sort of constructions. So we have these time evolution approaches, which seems to be quite promising, but are there alternatives? Are there other ways to incorporate some sort of information from the quantum hardware into the configuration sampling step? So we have sort of that basic first step being just the occupancies, but can we go beyond that? We then need a bit of theoretical framework around QSCI as well. It's sort of very much been a tool to get quick and dirty experimental results at scale out the door. So I think it needs a bit more of a sort of theoretical framework to surround it. And then again, try and do something that exceeds that sort of 100 qubit scale. Here are the sort of all of the different parties that we've worked with, as just to have them on there as an acknowledgement. And yeah, that's everything. Thank you so much for your time. I realise that took quite a long time. So if you have any more questions, make a second. It's a great question. So I think some of the largest QSCI calculations have gone up to like the 10 to the 10 scale number of configurations. I mean, so for example, just looking at the
And they're doing a Lanchos or something like that, or
Davidson, I believe. Yeah. So here, okay, so this was from the first HCI paper. They went up to 10 to the 7 determinants. That's for quite some years back now. So I think the most recent work from IBM, yeah, was something like 10 to the 9, 10 to the 10. I think they have aspirations for 10 to the 11. And they're working a lot with the Fugaku system, Riken. And so I think they've actually written some sort of bespoke sort of diagonalization solver for the Fugaku system. Fugaku is somewhat interesting in that it's a CPU only supercomputer. It doesn't have any GPU acceleration on it, which is kind of rare these days.
Yeah, if you've got sparse matrices, which you do, then the GPUs are nightmarish for branching. So
right.
So it's probably
yeah. So yeah, I think it's 10 to the 9 you can do. Beyond that, I think it's possible, but yeah, it requires some very heavy sort of HPC resources to achieve that. I mean, in our SI, the sort of the silane results, we only went up to like 500,000 configurations, I think, in the QSCI calculation. Partly down to my shoddy code. So you do like the ICF calculation goes like 10 to the 7 or so. I was capped at like 500,000 or so.
Oh, you're beating SCI, which has much more configuration. So you select much better configurations.
Beating which one, sorry?
You beat SCI. Yeah, you're beating ICF, so your configurations are much better.
Exactly, yeah. Which it comes down to this problem I mentioned though, where this sort of this implementation of ICF sort of takes this kind of like a Cartesian product of you have like an alpha, you have a set of like alpha configurations, set of beta configurations, it just multiplies those sets together.
Yeah.
So you need the flexibility to address configuration by configuration for the sort of alpha and beta electrons at the same time together as really compact representations, which is what HCI can do. Because otherwise you have sort of, potentially quadratically many unnecessary configurations in your wave function.
Like, do I understand correctly that QSCI is like the math is similar to HCI, right? Yeah.
Yeah, absolutely.
So, like, where do you expect the advantage of QSCI compared to HCI?
Sure. Yeah, I mean it's a nuanced question. I guess in these pictures, right, or any difference between HCI and QSCI, we've replaced this sort of step on the left-hand side there where you're contracting the Hamiltonian onto your wave function to get like a new set of configurations. That's now being replaced with something from a quantum device. Doing that contraction is really expensive, especially as the wave function grows in size. This is why the HCI people devised their sort of semi-stochastic approach to doing HCI to try and get around having to actually do that explicit contraction. So they have both a semi-stochastic way of sampling configurations and a semi-stochastic way of applying perturbation corrections on top of that as well. Whereas, it may be that we can devise circuits in such a way that we can probe those higher order excitation terms, but at a sort of lower cost. So here, for example, to get sort of excitations to like kth order, we need to go through k iterations of this process. Here, we might be able to get away with, I don't know, k rounds of time evolution or something like that. So we're trading the sort of classical cost to doing this contraction with the sort of circuit depth required to sort of construct these circuits. But there might be different ways of building these QSCI circuits as well. That's just looking at it through the sort of quantum Krylov lens, that sort of time evolution stuff.
Going to ask a question that might be silly, malicious, or both. We're just thinking about this trick of the occupancy biasing. Do you envision that someone in the selected CI community could notice this trick and adapt it to classical selected CI?
Yeah, I mean, potentially. I mean, I think that would be a good outcome actually if you could, this inspired some sort of better way of doing it classically. It's bad for the QSCI community because then it pushes the sort of the benchmark becomes even harder. Yeah, I am sort of more generally interested not just in QSCI, but also, if there are better ways of doing sort of conventional SCI as well.
To some extent, the heat bath approach, which has got an energy denominator on it in its selection process, does do a bit of that because so it's not fully flat, at least.
Right.
So it might look a little like this.
So you mean, yeah. So in the sort of, I didn't go into this the actual sampling protocol itself here, but it is sort of quite HCI-esque in the selection. So it does include, for example, the weightings of the wave function coefficients from sort of previous rounds. But then that's further biased by sort of these occupancy distributions as well. If there's a way of sort of refining the sort of selection criteria, I guess that's the sort of the great thing about HCI is because the selection criterion is so easy to evaluate. So it can be run at sort of pretty large scales. Yeah.
Okay, great. Thank you so much.
Okay.